Something else to keep in mind, to find the derivative, I did write down a general example here when we talk about ax to the n power, bx to the n minus 1 power, cx plus d. The way I wrote it down, this is just copied from your textbook. Oops, and I see that there's a little typo here. That should be f prime of x, not f prime, not x to the x power. The way your textbook writes it down is cx plus d. It doesn't explain what happens to this the d there, but you remember it would be like a times it should be a times n times x to the n minus 1 plus b times n minus 1 times x to the n minus 2, and then plus c times 1 to the x to the 0 power plus d times 0 to the x to the negative 1 power. And your textbook doesn't write that part down, and it's not important that you write it down either. It's just important that you understand where the derivative is going on those first powers and those 0 powers. When you have x to the 0 power, you're multiplying everything by 0, which is why that constant term goes away completely, which is why this plus d just disappears. All right, and that's why the cx just becomes a c. All right, because it's just the first power times x to the 0 power, and x to the 0 power is just 1. All right, so those are some important notes. We talked about a function increasing or decreasing, and you can look at a graph of the function itself and tell when it's like decreasing, when it hits a minimum, a local minimum, and starts increasing again. Or you can look at the derivative of the graph, and I think it's a lot easier to look at the derivative because then you can say, is it above the x-axis? That means it's increasing. Is it below the x-axis? That means the original function is decreasing. All right, and then any x-intercepts on the derivative would be turning points of your actual function. So that's a good note to put down, maybe, that I didn't really write down. But any x-intercepts on the graph of the derivative. Derivative, there we go, are local max or min values of the function. And it's still up to you to determine whether it's a maximum or minimum past that point. But those are local maximum or minimum values of the function itself. All right. So up to you to determine whether it's a maximum or minimum, and you can tell that by looking at the graph. You can tell that if it's going from increasing and then crossing the x-axis. If the derivative is crossing the x-axis going into a negative direction, that would be a maximum point. If it's crossing the x-axis from the negative side and going into a positive direction, that would be another example. And it is possible to have an x-intercept on the derivative where it touches the x-axis and then turns around, and that means it's not a local maximum or minimum at all on the original function. And you could look at the original function and see where it's kind of slowing down and then starts again. All right, so that's possible as well. So there's a lot of different outcomes we could have for these functions. So it's important to graph both the function and the derivative. And if you're stuck on anything on the test tomorrow, that's my best advice. Graph them. Graph them both. Okay? But you got to be good at finding the derivatives, otherwise you're going to be having a problem on the test tomorrow. Because that's the biggest concept in the whole chapter. Can you find a derivative of a function? All right? All right, the derivative of a function at any point represents the gradient of the tangent line at that point. Gradient means slope, remember that. Your textbook uses the word gradient the entire time. It never uses the word slope. But we're used to the word slope, so that's what we want to talk about. So the derivative of a function at any point represents the slope of the tangent line at that point. All right. And remember, the tangent line, you can draw a tangent line at any point on the graph, and you're going to find the slope of it by just plugging into the derivative value. Okay. The x, plug in the x, find the y value of the derivative. That's your slope. Okay. So anything else about here? Let's see. A stationary point is a local max or min. And then we talked about The local maximum is when the derivative equals 0. That's when it's crossing the x-axis. And it says the local maximum or minimum point may not be the maximum or minimum values of the graph. So it might not be the absolute max or min. That's what I mean by that point. And then if the sign of the derivative goes from negative to positive, there's a minimum point. If the sign of the derivative goes from positive to negative, there's a maximum point. So this whole box right here is kind of what I was talking about with the red ink over on the right-hand side. All right. And then the last thing we talked about in section 12.3 was if a function is to be optimized, all right? And if we use one variable, then we can graph it directly on our graphing calculator, or we can graph it on Desmos. If we use more than one variable, then we have to find some type of relation between the two variables. Like we did an example on Tuesday where we did the radius and height of a cylinder. And remember, we had to solve for height, so that way we could put everything in terms of one variable only, and it was all in terms of the radius. And then we were able to find the derivative and do all the work we needed. And at the very end, we plugged back in and solved for the height. So that's what I mean with optimization problems where there might be more than one variable. So that was our last example on Tuesday. For those of you keeping score at home. So remember, we do allow open notes. So really important that you go back to your Tuesday notes and think about that. That was our last example with the radius and height. So just make sure you're comfortable with those types of problems where we might need to solve for one variable and find the derivative and all the information from there. All right. Now, with that being said, I went through everything pretty quickly, threw a lot of word vomit at you. I apologize. What we're going to do today is I just have some practice problems. There's no assignment. It's just the worksheet itself. So in class, I'll record the notes and I'll post the worksheet answers. But this is really good practice for the test tomorrow. It's not going to be exactly like the test, but it's going to have some similar difficulty problems. So make sure you're okay with this review. I see a little typo on number 2. It should say find the equation of the normal line, not the equations of the normal line. All right, so go ahead and start working on these problems. I'd recommend let's start with problems 1 right now. I would say find f prime of x first. And then find f prime of -1 of each of these. That'd be what I would start with first. All right, so start with problem 1, and we'll work through these problems a little bit at a time, but work through it at your own pace today. Before I can find f prime of -1, I need to find f prime of x. And before I even do that, it's not a bad idea to rewrite the problems. So like part A, I had a 2 over x there. So I went ahead and rewrote it as 2x to the -1. I went against my better algebra judgment and undid some work. Because in algebra, we like to not have negative exponents. But in calculus, negative exponents aren't such a bad thing. Okay, so make sure you rewrite it first, and then we can go ahead and find x prime, f of x prime. And when I rewrote my final answer down here, I wrote it as -2 over x squared, because personally I think it's easier for me to plug in values with that x squared in the denominator. I don't get confused by the negative exponent. You can leave it as -2 times x to the -2 power. That's perfectly fine. It's entirely up to you. But for me personally, I like working with this a little bit more. So it's entirely up to you which one you want to use. And then we go ahead and plug in 1. And I ended up getting, f prime of -1 equals -6. You should be able to graph your function and verify that's the correct answer as well. Graph f prime of x and just type in x equals -1 and see that you get the point -1 comma -6, and that proves that you did it correctly. So you can double check your answer and you can walk away confidently knowing I got the right answer on this one. That's good to know. Whoops. For problem 2, or part B, when I rewrite it, I just simply rewrote it in descending order because it wasn't in the correct order before. And that's just going to help me keep track of the variables a little bit better. And then I went ahead and solved. I got negative 30 x to the 5th minus 25. And all that happens when I have a negative 1 to any power, like it's the 5th power here as well, it's just going to change the sign of the function. So because negative 1 to an even power, like squared, is going to be a positive 1 to the 3rd power is negative 1 to the 4th power is positive 1 to the 5th power is negative 1. The sign just keeps changing whichever power I go to. So I just saw an odd power and I knew that was going to change the sign of the whole function. So that's how I got a positive 30 there. And then I get 30 minus 25, and I get f of prime of negative 1 equals 5. And again, graph that with your final derivative function, and you should hopefully see the point negative 1 comma 5 on your graph, all right, to prove that you did it correctly. All right, for problem 2, it says find the equation of the normal line at x equals 3 for f of x equals x cubed minus 2x squared plus 2. All right, so one thing I'm definitely going to need for this problem is I'm going to need an ordered pair. Right now I don't have an ordered pair. I have an x point, x equals 3. How do I find a y value on a graph if I'm given an x value? I just simply plug it into the original equation. So that's going to be the first thing I want to do for something like problem 2 here. Let's go ahead and solve and find the y value. If it's not given to me, I should be able to solve it really quickly and do that. And just figure out what f of 3 is. So I get 11. So my ordered pair is 3 comma 11. That's the first thing I need. That's step 1. Step 2, I didn't give myself enough room. Step 2, I need to find the slope of the tangent line. Or gradient, depends on how you want to say it. That's step 2. So find the slope of your tangent line. That means you need the derivative of this function. So I need to find the derivative of the function so that way I can find the slope of the tangent line by plugging in that x equals 3 value into it. Okay, and then step 3, I should be able to find my slope of my normal line. All right, so I'm going to give you guys a couple minutes to figure it out from here. Give this a try. Remember to look back at your notes. I think we did this one on Monday this week. It might have been Friday last week, but double check your notes. Remember, it's open note test tomorrow, so rely heavily on your notes. Make sure you're comfortable using those. So take a minute to work on this problem now. Get a reciprocal of that. So I find the slope of the tangent line by finding the derivative and then plugging in the 3. Slope of the normal line is the negative reciprocal of that. Negative 1 over 15. All right. That's how I find the slope of the normal line. And then we're doing the normal line. We're just going to say y equals mx plus b. Well, we know the slope's going to be negative 1/15. And then I've got the point 3 comma 11 that we found at the very beginning of the problem. It was 3 comma 11? Yeah, 3 comma 11. And now I can say 11 for y, and I'm going to solve for the b value to figure out where the y-intercept's going to be for this line. All right, and now it's just a simple solving problem. 11 equals negative 1/5 plus b. I'm going to add 1/5 to both sides. And, sorry, question?
It's 1/15.
Well, 3 times 1/15 is 1/5.
Oh, gotcha.
Yeah,
Fine.
sorry, I did a little substitution there. I skipped a step. I apologize for that. So I distributed that 3. Okay, I add 1/5 to both sides, and 10/5 is 50 over 5, so it's 55/5 plus 1/5. So I should get 56/5 equals b. You might be able to write as a decimal as well, which is fine. So our final equation now is negative 1/15 x plus 56/5, or 11 1/5, and that would be our the equation of the normal line. All right, not the equation of the tangent line, but the equation of the normal line. So as long as we know the difference between the two, just remember whatever the original function was when we graph that x cubed, it's going to look something like this. And what we just did is we said, hey, the tangent line is going to interact at this 3, 11 or whatever. So here's the tangent line with a big steep slope of 15. Our normal line runs directly perpendicular to that. It's going to look something like that, perpendicular to that tangent line. All right, that's what the normal line is. Okay. So there's our normal line, there's our tangent line. That's what we do for problem 2 there. Okay, can we identify one or the other? So tomorrow on the test, you should be able to write an equation for both the tangent line and the normal line. That's a lot of steps, but that's probably the hardest concept in the chapter, is trying to write something like that, maybe between that and the optimization. All right. Problem numbers 3 and 4, I'm going to give you guys a few minutes to work on both of those. So problem 3 just asks for what interval or intervals is f of x increasing, and then for what interval or intervals is it decreasing. Find the coordinates of a local maximum or minimum and label them as such. It doesn't guarantee that there's going to be one of each, but find those coordinates if there are. And then for problem 4, x squared minus 9 over x, go ahead and find the derivative at f prime of 3. So that's very much like number 1, okay? For problem 3, what intervals is it increasing? Who's got the intervals for increasing and decreasing for problem 3? I'm just curious what we got. So we should be able to graph it and tell, or find the derivative, and that's going to help us identify the increasing and the decreasing a lot faster. So I'll write down the derivative first, but anyone got it? They want to add it in the chat or share what they have for the intervals? Increasing or decreasing? Or you can unmute yourselves and share. All right, so increasing from 3 to 5. All right. And does that mean it's decreasing from negative infinity to 3? And then yeah, that's good. And good use of the union and everything. And 5 to infinity. And I think when we say decreasing or increasing, we'll just want to say 3 to 5 in parentheses as well, or the reverse brackets, just because at 3 it's actually 0, it's not increasing or decreasing at 3, and at 5 it's at 0. Okay, and then find the coordinates of the local maximum or minimum values, and again you should be able to tell that from your graph. So it looks like there should be a point.
And we find the intervals from graphing it too, right?
Yeah, you should be able to find all of this from graphing it and looking at the graph. Yeah. So it's just basically, can you read the graph, or can you identify the derivative and do it algebraically with the derivative as well? So that's the other thing we could do. Okay. So the coordinates of the minimum and maximum, you should be able to find those on the graph. One of them is going to be 3 comma something, and the other is going to be 5 comma something. I just don't know what they are off the top of my head, because I did this problem the other night, but then I forgot to write it down. So the min is 3 comma negative 4, thank you very much, and the max is 5 comma 0. That's a local min and a local max. And then we'll have some increasing and decreasing around that as well. Okay, so x squared minus 45x plus 50. All right, great. Yeah, so it just has a very small increasing range. And when you graph the derivative of it, it makes it look really easy to tell when it's increasing, when it's decreasing. That's why we love derivatives. Really easy to tell when it's above the x-axis and when it's below the x-axis. All right. Problem number 4, find the derivative and f prime of 3. So first things first, I'm going to rewrite f of x as x squared minus 9 to the x to the negative first power. And then I'll say f prime of x equals 2x minus plus 9 to the x to the negative 2 power. And then just because I prefer it, I'm going to rewrite it as 9 over x squared. And now I can plug in 3. 2 times 3 plus 9 over 3 squared. So I get 6 plus 9 over 9. And I get 6 plus 1, so I get 7. F prime of 3 equals 7. That was my answer for problem number 4 there. All right. Last couple problems. The equation of a curve is this y equals the gradient of the tangent to the curve at point P is negative 10. So what's that telling us when I tell you the gradient to the tangent is negative 10? What's that information telling me right there? It's important that we know what that means. So if we start with this thing, f of x equals x to the 4th minus 3 halves x squared plus 7. This is saying that f prime of something equals negative 10. All right. So we know the y value, but we don't know the x value. That's what this is telling us. Okay. So it's giving us the gradient. We know the slope of the curve, but we just don't know what the x value is going to be. That's what this problem is telling us. So first things first, let's go ahead and find the derivative of the function. So it's going to be 1/2 times 4x cubed minus 3 halves times 2x, and then the 7's going to go away. All right, so 2x cubed minus 3x. All right. Okay, now we know that's going to happen when this equals 10. All right, so we could solve it this way by finding out what values of x are going to give us a y value of negative 10. The other way we could do it is we could just graph the derivative. So I'm going to graph 2x cubed. Oops, I said negative 2x cubed there on accident. That's a mistake. Graph 2x cubed minus 3x. So I'm going to do that first. So let me share my screen with you. If 2x cubed minus 3x, and then we're going to graph the line y equals -10. And there's the intersection. So that's going to be the absolute easiest way to do it. Hey, x equals -2. All right, so we got to be able to use our graph in order to do that. Okay, so remember this -10 is telling us that's the slope of the line on the original function. So now, if I go to the original graph again, 1/2 times x to the 4th, we'll go ahead and graph this thing, minus 3/2 x squared plus 7. I now know that the y value, or the x value, is going to be at -2. So -2 is going to be somewhere over here. So hopefully, we'll solve algebraically, but we're going to find out what the, there it is, what the y value is. And it looks like it's going to be about 9, but we'll prove that algebraically, that the y value is 9. And that's where point P should be, is -2, 9. Okay, that's kind of the goal here for this particular problem. So I found the x value. Now I just go back to the original function and say f of -2 equals 1/2 times -2 to the 4th minus 3/2 times -2 squared plus 7. And now I get 1/2 times 16 minus 3/2 times 4 plus 7. Oof. I did not give myself enough room. I apologize for that. So I get 8 minus 6 plus 7, which is 2 plus 7, which is 9. So I proved it algebraically. I already checked it on the graph. I already said it was going to be -2, 9. So point P is -2, 9. That's the idea for this one. I got this slope of a tangent line. All right, so it means I need to find the x value, and I can just do that by graphing. Just, hey, let's find the derivative, graph it. But pretty much whenever you're stuck on any of these problems, the first thing should always be find the derivative. That's the whole point of the chapters, find the derivative of the function. Okay. All right, last problem here. It says a company's weekly profit in dollars in relation to the number of units sold each week, x, can be modeled by the function f of x equals -0.9 x squared plus 52x minus 360. Find the maximum profit and the value of x for when this occurs. Okay. So we want to find the maximum profit and the value for x when this occurs. Easiest way to do this one is going to be to graph it. Graphing could be a little bit tricky though, but another way we could do it really fast is find the derivative again, -0.9 times 2 plus 52. So f prime of x is -1.8x plus 52. And if we find when that equals 0 right there, we're going to find the x value of this function right off the bat. Turns out for this one, we subtract 52 from both sides. And I'm going to divide by -1.8. All right. So 52 divided by 1.8, that's going to be slightly bigger than 27. 28.9, something like that. 28.8 repeating. That's the x value. And then I can go back and plug that into the original equation to find the maximum profit, because I know this is going to be my maximum value. All right. plug it back into the equation, find the maximum profit. Plus 52 times 28.8 minus 360. All right, that's the idea for the very last problem here. Okay. And then just work through it, figure it out, double check on your graph. So let's graph it, verify that we double check it, and that we did everything correctly. All right. But again, knowing how to use a derivative, in this case, I know that if I set the derivative equal to 0, that's going to be when there's a slope of 0, and that's where the turning point's going to be on the original function. And I want to do that too because I know with this weird graph, it's going to be really hard for me to find a scale. So that's why I think it might be useful to find the points themselves algebraically. It could be really hard to find the scale to find that maximum value on a graphing calculator or something like that. So it turns out when I do 28.8, I get 391.1 and the 1 repeats. So it's safe to say that $391.11 profit is the maximum profit I'm going to make. Okay. And that occurs when x equals 28.8. So essentially, if I'm selling 29 units, I'm going to make $391. All right, that would be the moral of the story here. All right, that's the most units I could sell. All right, so actually it wouldn't even be 29, it would be 28. I had to round down for this one because I don't quite get to 29 units. All right, once I'm at 29 units, I'm actually down a little bit more. Yeah, just a little bit below that line. Anyway, that's the idea for this last problem.